All right, so let's talk about some design principles, some best practices, and the idea is, in general, the idea is that we're working with very complex systems, and we would like to be able to break them up into smaller chunks, right? So that we can understand a smaller problem, but then at the same time, so that it can collaborate with other systems, so that we can actually solve the bigger problem, right? So we have this balance of simplifying, right, so that it can fit in our heads, in our limited minds, but nevertheless that we can abstract and look at it at different layers of abstraction, so that we can once we understand some of the details of the lower layers, we can wrap it in a very simple terms, and combine it with with other simple modules to create ever more complex systems as we grow at different layers of abstractions. Any framework that you want to use should support the capabilities of doing that, right? And object orientation, introduce the idea of inheritance and being able to use interfaces, and all these ideas were geared towards being able to break up and deal with the problems at different layers of abstraction. Also the other idea would be that something that we have solved already, we would like to be able to perhaps generalize it in some fashion that perhaps we can reuse it, perhaps parameterize it a little bit, and then reuse it in a different context, right? So again, the idea of reusability, being able to break it up, right? Reuse them as kind of like Legos components that you can build in something more complex. So object orientation had this initial intent, right? Break up, abstract, right, and then build up more complex systems. Also, the once we enforce these ideas, languages evolved to support these object orientation ideas, but they weren't even though they enforced certain good practices, there was many other things that we discovered even using our own these languages, and there were certain styles that we have identified as patterns of good practice of how we should implement things, and we've slowly accumulated a body of good practice and design patterns of things, how you should do things, how you should not do things, and with the idea that these patterns, once we have these mental models of the design pattern, folks can very quickly sort of understand how things are organized, right? Like, for instance, if somebody says, "Oh, it's a client-server architecture," immediately, certain things come to mind, right? Okay, probably is HTTP. You have some client running that is sending some HTTP requests, and then a server that's responding. So just the notion that we can say just a word, and immediately certain ideas pop up in your head is very important on how things are organized, what you can expect. Or if you say it's an MVC, model view controller. Okay, all right, so this controller that's listening for incoming requests is using kind of service layer and whatnot. So immediately these patterns pop up into your mind, right? So same thing. There's and like that. There's tons of design patterns and best practices that if immediately says inversion of control, you should pop into your mind. What does that mean? What are the benefits, right, of using such patterns, right? And then we create a vocabulary of these patterns that we can now understand what are we talking about, what good practices, why do we do it, right? Why is it a good thing to do? Now, just like languages caught up to the idea of object orientation, languages have kept evolving, allowing to implement other ideas such as component technology and inversion of control or injection, right? So Java now supports injection and AutoWire and whatnot, where you can you define all these services and they're magically injected into your source code. And languages will keep evolving promoting or enforcing certain architecture, certain design patterns, right? If you've done React or Angular, you might have found that perhaps a little bit restrictive, that it forces you to think in MVC, and if you try to move away from that design pattern, it kind of works against you, right? So it forces you into a particular best practice, but then some folks might feel that it's a little bit too restrictive, right? So same thing, right? So languages try to enforce certain practices, not all of them, right? But they'll keep evolving over time. And the idea is that it makes it easier for everybody to maintain everything, right? Immediately, they know where things should fall, right? And where to look for things. It makes it much easier to increase the efficiency of the overall efficiency of the team. So some principles that object orientation had in mind is abstraction. Can we describe a solution at different layers of abstraction, so that maybe at a very low level I'm talking to the directly to the file system, or directly to a database or network. So I'm talking presumably to a very low layer of abstraction, whereas at a very high level, right, I might be thinking about the problem in a very abstract sense, right? And in between, and everything in between. Can we create a hierarchy that allows us to break it up and think about the problem in very different layers of abstraction? So certainly abstraction, encapsulation. Can we create these systems so that different concerns are not affecting other parts of the system, right? Where our changes might be local, and any local modifications that I make are not affecting other parts of the system. That if I make a mistake here, or I have a local variable, it doesn't have side effects on other systems, right? So certainly we've evolved, and for instance, we don't use gotos anymore, right? And we don't use certain aspects of programming, again, because we want to minimize the effects of any change that we make, right? So that makes it easier to debug. If I run into an issue and I see something crash, or a particular line of code, hopefully my solution will be within those lines of code. I don't have to backtrack and see what other side effects are out there, right? So certainly we've identified the benefits of encapsulation, modularity, being able to break it up into small pieces that can be reused, can be parameterized, right, and build it into ever more complex systems. And hierarchies, again, that allows us to break it up into perhaps inheritance or aggregations or compound data types that can be built into more complex ones. Right. So object orientation looked to enforce these principles. By abstraction, we meant that we need to decide to deal with a problem at its right level of abstraction, right? Meaning a problem can be as detailed as you want, right? But there might be many details that are not relevant to solving the problem, right? So depending on the domain, you might care about the minutiae, right, the details, but in some other domains might not. So, for instance, if you're in a university and you need to model a car, it might be that your level of abstraction is enough that the license plate is enough and the car model is enough. That's it, just those two pieces of information. But if you're in a different context, a car might be represented. You might need much more detail, right? So if you're a car manufacturer, then a license plate and the models might not be enough, right? You might want to go all the way down to the minutia of the bolts, right? That are so your data models will be completely different. Your representation of a particular idea will be completely different, right? Depending on the domain. So depending on the domain, you need to choose how detailed do you want it, right? Do you need to know that it's a Tesla and it's a Model S, or just a box and a couple of lines? Is that enough, right? Here's another idea. Do you need to know exactly the entire map with all the buildings and the trees and whatnot, or is it enough that this perhaps might be for different uses, right? Some places I might see a coastline with a beach and whatnot, whereas over here I might just have blue and yellow, right? And I don't know if it's sandy or not sandy, right? So depending on what the question is, you might want one model representation versus another. So yes, so definitely different layers of abstraction for different questions, right? For different domains. So abstractions identify these kinds of granularity, right? What are the common aspects or attributes or properties that you want to keep track that are important in your particular domain, and it's you who decides whether something's important or not. You know, depending on a game, maybe gravity might be important to represent, right? If you're doing a platformer, perhaps. If you're doing a checkers or then maybe gravity doesn't matter. Again, so depending on the domain, and it also allows you to understand this without being bogged down with the minutia, right? We are abstraction animals. We like to create these abstractions, and once we understand something, we become bored of it. We put it inside of a box. And then forget about what's inside, right? We just treat it as this consumable, right? And then we create something more complex, and again we box it up, and then we forget about the details inside, right? We create an interface, and that's all we really need, right? So a car for us is just the interface, right? Just a stick, a couple pedals, and a steering wheel, right? We don't care about all the details that go inside the car. Just the interface is what we care about. Right, and that's all we really might need for understanding for our purposes. We don't really care about the concrete without having to know the details. So it's abstraction is identifying what are the essential characteristics that I need for my domain to be able to answer the particular question, and what are the boundaries and what are the interfaces or any other dependencies that my particular abstraction might have with any other systems that it might be interacting with. And again, from two different folks looking at the same, at the same reality, right, might have a different abstraction of what they're looking at, right? Some folks, consider our minds as an abstraction machine that represents the world, for us, for our minds, from moment to moment, just clearing out lots and lots of noise that is happening, right? We only live in this interpreted reality of what actually is there. The world's very, very noisy, and our eyes and minds, tried our best to, just clear out those noises. So throughout the lecture, there's several references to a temperature sensor that goes on and dips a sensor into these hydroponic and keeps track to make sure that the plants are in with the correct humidity and temperature. So throughout the lecture, there's a couple examples on these representing what these temperature modules might be, sensors might be. So it might be that you're writing the libraries, right, that deal with the real-time measurement of a thermocouple, right? And for you, it's a particular address space, right, in the CPU that you're reading from directly from memory. So you're way down in the weeds, right, at memory management and whatnot, and so you're way down in the details. So for you, your layer of abstraction, it might be that you convert these zeros and ones and hexadecimal code. For you, that's the abstraction, the hexadecimal code and some address. But even that is an abstraction, right? The CPU itself is an abstraction of some virtual machine, right? Of some zeros and ones that are being represented in some register, in some RAM, right? That's even a layer of abstraction. So again, anywhere you are, right? You can draw an arbitrary line of abstraction. Okay, just that the fact that we call this an int or short, right? Even that's an abstraction. Yes, that we don't want to deal with the bytes, right? So we create an integer, right? That abstracts the fact that there's so many bytes in an integer, right? And we want to treat it somewhere we draw the line. We won't go any down below that. We don't want to be in you might as well be in assembly language or machine code, right? So this would be an engineering's understanding of perhaps the layer of abstraction. Maybe this is enough, right? But somebody on top of that might want to create a wrapper around this, right? That could be used at a higher level, right? So that you don't have to deal with addresses and whatnot, right? So somebody might wrap it with a nicer interface, right? That might have these APIs that you just call it, right? The current temperature, and comes back with an object, right? That contains the degrees, and maybe it gives it to in Fahrenheit and centigrades and all the conversions that you might want, Kelvin, and the location of the measurement, and also the calibration that you can give it an actual value for the temperature, so they can calibrate the thermocouple. So again, this would wrap and create an additional layer of abstraction, and depending where you are in the abstraction layer, it might be that if you're way down in the abstraction layer, you might be creating very generic lines functionality, right? Because you don't know who above you is going to use your library, right? You don't know what kind of applications they're going to use, they're going to implement. So you become very generic. You try to write extremely verbose APIs, extremely verbose functions, right? But the higher level abstraction you go, and you start getting more vertical, right? Where you use a particular library to create a particular solution, right, for a particular domain, right? So if you're writing graphic card APIs, right? You don't really know what kind of games anybody's going to be using, right? So you're very generic, right? But once you get into a particular vertical, right, you become more specialized, more specific on what kind of APIs you're willing to write and provide or consume. So here's a funny example of abstraction and what we mean by reality or interpretation. So yeah, this is a pipe. You would say, so this goes into a more philosophical taxonomy of classifying objects, right? So yes, this is not a pipe; it's a projection of a picture of a pipe. But you can certainly get into many philosophical discussions about reality. If you have a boat, what is it? If you have a boat and then you remove a piece of wood and if you replace it with another piece of wood, is it the same boat? What if you replace all the pieces of wood? Is it the same boat? Or you lose tons of cells throughout your lifespan, and by the time you're 30, you're completely different. Your entire cells have been replaced. Are you still the same person? So anyway, so we're not going to get into those philosophical questions. So abstractions, right? Definitely abstraction helps us to deal with problems at different layers of detail. So the other idea that object orientation promotes is the encapsulation, right? That we should keep as much as possible the information, control the access to information as much as possible, and only give access to a limited set of friends that might want this, right? And kind of implementing the idea of information hiding, right? Where we don't allow other folks that are outside of where the data is being kept to have unfettered access to the data itself, right? Instead, we provide interfaces, right, that validate any changes, make sure that any object is always in a consistent state, right? So certainly we certainly implement that using private or protected or public, right, in our interfaces, so that all changes to any variables inside of a class would only go through a public interface, and all the data types would be implemented, all the variables would be implemented as private. So the idea is to implement the the policy that changes should be local, right? And we should not be advertising this anywhere else, right? Right. So we want to compartmentalize, and any data or the structure or behaviors, any of the functions are inside of the compartment, so that they're not exposed to any outside access, right? And also one of the other ideas that falls out of this is that interfaces allow you to declare the behaviors, right, and separate it from the actual implementation, right, where you can advertise what the interface is, right, either in a .h file, right, where you give the signatures of your functions, or an actual interface in Java or .NET, right, and folks know the interface, but they don't get access to the implementation, and you're free. This frees you from committing to a particular implementation, right? That this allows you to independently implement your algorithms in the future without breaking somebody else's using that interface, right? So if your data access layer, for instance, you had written it in such a way that was accessing MySQL, right? Your same interface could stay intact, and underneath you would perhaps decide to now use a NoSQL database, right? And no one would know, right? Because everybody's compiling against an interface, right? And you're free now to decide that you might have multiple implementations. And this is exactly what JDK, the JDBC folks do, right? All your code is implemented and compiled against the javax.jdbc.whatever package, right? That declares interfaces such as connections, statements, result sets, and whatnot, and prepared statements. But the actual implementation is implemented either by MySQL or by SQL Server or by Oracle or by whatever, right? Whatever vendor implements it. But your source code doesn't have to change because you're compiling always against an interface. So this separation of interfaces and implementation, right, allows you to shield your large portions of your source code from changes going forward in the implementation, right? So what it does is it decouples, right, pieces of source code that they're no longer they no longer depend on each other, right? You could certainly just remove the MySQL jar file and just replace it with the Oracle jar files. You just change a couple of configuration files, and your source code should just work just fine. That's extremely beneficial and allows you to be much effective and make yourself much more nimble at how you can implement these things, right? So another idea from of decoupling different parts of the software is that the idea of an observer, right? That there's certainly going to be intercommunication between multiple systems, right, or between different classes that need to know about certain events, right? So the idea of the observer, you try to address this need of communicating between different classes by implementing somewhat what a pub-sub architecture might have, right? Where you try to create an asynchronous communication as opposed to a synchronous communication, right? So imagine comparing a phone, right? If I call you, we're talking to each other synchronously, right? I talk, you talk, I talk, you talk, right? It would be very awkward if somebody just doesn't say anything for quite a while, right? And just lets me hanging there, right? We're consuming a resource of having a live connection, but we're not saying anything. It would be very awkward. So it's meant to have a very coupling effect between us two. I'm waiting for you, and you're waiting for me, and I'm waiting for you, and I can't do anything else, right? I'm talking to you, as opposed to a much more asynchronous communication where I send you an email or I send you a text. You're free to consume that at your own pace, right? you can get to it. Maybe it's in a queue, and you're busy doing something else, and you then can come consume it at a later time. This increments the overall efficiency of both places, right? Imagine so the idea of having these queues or these lists of folks who are interested in some message, right? It creates these asynchronous, this decoupling between two systems. It's very, very beneficial. Imagine going to you go into Dunkin' Donut and there not being typically when you go there is a queue of donuts, right? Imagine there was no queue, right? I go and I ask for the donut, right? And I have to go and make the donut, right? And make the donut, they come back a couple minutes later, here's your donut, right? And then you take it and you consume it. That's very awkward, right? That doesn't work. So the way they decouple the two systems is they have this basket, right? That is full, somebody fills it in while somebody empties it, right? So the observer pattern is based on this idea of decoupling two systems, right? That if you want an event and you want to be notified of something happening somewhere else, you register. You say, hey, I want to register for this particular event. I'm implementing a particular interface, so presumably you can call me, right, at a particular function that I'm implementing, and I register. It says, hey, I am an observer. Add me as a register observer. And then when events occur, this keeps track of a list of observers who have expressed interest in certain events, right? And when the event occurs, the observer pattern just iterates over the list of observers and then just notifies them, hey, this happened, because you want to know, right? And that observer can then maybe unregister because I don't want to know about that anymore. But this decouples the pieces of source code as opposed to having to instantiate you, right, and call you, right, and then you're returning, and then I throw you away, right? So that would be very coupling, right? We need to know exactly. We need to keep track of an instance of you, right? This decouples that from there. So we register and then we send notifications to anybody who had declared any interest in that event. Other best practices is that obviously source code information is going to change over time, and typically we want to be able to compartmentalize that, right? Perhaps in either a configuration file where we might have multiple constants, right? That we don't have to have these magic numbers everywhere, right? That we change over time. We have one single place where we can maintain that in a single place, either as number literals or strings or XML configuration or JSON files that might keep track of all these constants over time as they change. So for instance, instead of using these hard-coded constants and magic numbers of 100, 99, 0, and whatnot, you would put in a centralized configuration file, and you would have constants that would be available throughout with the values that you can change over time, right? So instead of 100 size equal 100, you would keep track of these values, and it would be an abstract representation as opposed to something that specifically represents that other value, right? So size as opposed to 100 and whatnot. Okay. So these are just minor best practices. Same thing here. Sales tax. You would declare 1.06 and then use that declaration elsewhere. Typically, either in one particular static class with all these configuration, or it could be a properties file, right? Or it could be a bean that would keep track of all these instances, or a singleton that keeps track of all these values. So here's another one where you have the 100 is converted into a boiling point, or even the messages as well. Right? The messages as well are stored in particular string properties files, right? Or even in XML. And that would even allow you to introduce other ideas as, for instance, internationalization, right? Where you have all the strings, all the all the headers and messages, right, stored in a properties file, right, that are represented perhaps in English or some base language that you can then send over for translation, right? And somebody comes back and they give you a Chinese version and a Hindi version and a French version, Italian version, right? And now your implementation of handling boiling would look up these strings and represent it and show it at a particular index by the current locale, by the current the preferred language would index this set of constant strings and then represent and display the correct values in the correct language. So yeah, so abstraction is good, configuration is good. Right. So the other idea was of making modules, right? So again, we are abstraction animals. We like to put everything in a box, in a classification. Perhaps that's why we're also somewhat prejudiced, and we have our own biases, and we are the results of our own biases. We can't help it. It has kept us alive for many thousands of years. If you see something shake under in the bush, you immediately think it's a snake or something, and you jump. You're not waiting to see if it really is a snake there that's going to bite you, right? So you make very, very quick decisions. So all these biases of wanting to classify things, has given the capability of creating and breaking up things into its smaller pieces, and being able. And the idea would be that we would be able to put them together to create ever more complex systems. Perhaps we've reached a level of abstraction that we no longer understand, how many of our systems work. Right? Operating systems is one of the most complex systems that humans have created. It's a miracle that my operating system is even working. And so many we create so many complex systems. What is it? The Falcon 9 Heavy. It's an extremely complex system, and many years of designing it, and hopefully won't blow up on its first trial. Did it try firing it? Anybody know? Not yet. Okay. Standing up. Just standing up. They were trying to fire the engines to see if it even fired. Anyway, so presumably it has lots and lots of little modules, right, that work together, and you have tons of these millions of moving parts, right? How could you possibly measure the risks of this thing, of any assurance that this thing is even going to work, right? So many things could go wrong, right? It's just bewildering on how we can track and attack so much complex systems. So ideally, what we'd like to be able to do is that each module is so simple, right? It only does one thing very well, right? That we can very easily just by naming it, we know already what it's doing. Okay, that we don't have to look at the details of what's inside, right? And that it can be revised and tested and validated independently outside anyone. Independently from all other modules, right? That you should be able to write unit tests, right? That it's written in such a way that can be tested from the get-go, right? That I can send it certain data, right, and validate that it's behaving as expected, right? And once I have a level of certainty and confidence, I might then perhaps associate it with other modules and create something even more complex. And the idea is that these modules they would be reusable, right? And that they could share data across multiple modules, right? Kind of like in the holy grail of the software bus, right? Typically we look at what electrical engineers and electronics engineers have as by the way of buses, right? Where they have multiple electrical systems just because they're so standard, and they know that if they plug in into a particular bus, they know that one pin has power, another pin is ground. So many pins are the data, the data axis that goes in a particular clock speed and whatnot, and things just work. You just plug it in and it just works, right? And that's kind of what we're looking for in the software world. We would love to have these kinds of plug and play software buses, right? We just drop in a class, and all of a sudden it just works, right? And we're sort of there, right? J2EE and .NET and these other competing frameworks, that's what they try to do, right? There's component technologies. Presumably, if you write your source code in a particular fashion, following a particular framework, you should be able to just drop in your Java class, right? And it just works. You just drop in your class, and it's multi-threaded. It's protected with some security. It automatically stores itself into a database and reads from a record. And all these magical things just all of a sudden happen, right? And so that's where we want to be. And so these modules, if you follow certain criteria, certain interfaces, all these magical things come to you, right? And the idea that these would be loosely coupled, but usually this kind of goes against another of the goals is that yes, you want it to be loosely coupled, but you also meaning it can behave consistently independently of everybody else. So it doesn't depend on anybody, but it also would like it to be very collaborative with many other modules. So the two things kind of go against each other. So yes, you want it to be self-contained, but you also want it to be very reusable with other folks in the same bus, right? So these two goals oftentimes conflict with one another, right? That you want it to be very collaborative, but you want it to be self-contained. So it's always like a balancing act, and how do you design these things that yes, they're self-contained and they hide the information, and they're not advertising the inner implementations, but they also we want to be able to cooperate and collaborate across multiple abstractions, right? So they're somewhat conflicting goals. So how is it that we decide on what modules, what classes, what methods go with one another? We certainly want to see that the groupings make sense, right? If you're grouping methods inside classes, if you're grouping classes inside of packages, if you're inheriting classes from other classes, or you're implementing certain interfaces, that the grouping makes sense, right? That there's a logical cohesion, that they all belong together, right? So if you're storing and accessing and interacting with a particular table, presumably all the CRUD operations that would store, read, update, delete would all go together naturally, right? They all fall within the same data layer class, right? Or if you have multiple classes that are implementing an association that are updating multiple tables, then that would be perhaps a grouping of multiple classes dealing with the individual tables, but then the association grouping together the two classes that interact with the individual tables, right? So that kind of gives you kind of like a hierarchy of how you would group these together, that there's somehow there's a cohesion, right, between the things that go along with one another. Weak coupling, by either implementing interfaces that can be swapped dynamically, even swapped at runtime, right? That you can decide at runtime what version of the interface to pass dynamically. If you want that, then perhaps there were certain implementations that would allow you to do that, or other implementations that wouldn't allow you to do that, right? So, for instance, if you implement inheritance kind of forces you to follow a particular inheritance hierarchy, right? And you would kind of inherit lots of behaviors that perhaps you weren't interested in as much, right? As opposed to using interfaces that allow you to choose, which ones you're going to implement, and several different classes that might implement the interface in a different way. and you can on the fly dynamically choose which implementation you want to use at runtime. And the other aspect or principle for modularity is the law of Demeter or the LOD principle of that's sometimes referred to as the "don't talk to strangers" principle, right? That only talk to friends, anybody you know, within your circle of influence, right? That don't go too far out from your immediate family, right? So we'll see several examples of these. So first one, let's look at the first principle of high cohesion. So yeah, as I mentioned earlier, right? You might have a set of functions, a set of behaviors that naturally fall together or belong together. If they're accessing a particular data layer or accessing maybe a particular interface or a particular API that's connecting to either Facebook or connecting to some data service out there that allows you to search a data set or retrieve an individual element. Those certainly would fall together or would be implemented together inside of one single interface, one single service, or one single data layer, or that they're implementing on the same data type, that would be implementing maybe multiple CRUD operations on the same data type, or just naturally feel that they should go together. Poor duckling. And weak coupling, we mean that again, either using an observer pattern or using a pub sub or using an interface where you never actually use the actual implementation of the classes, as opposed to you always compile to interfaces as opposed to compiling to actual implementation classes, right? And then you have the actual behaviors, the actual implementations implement the interface, right? And this gives you the ability of working on the actual implementation independent of who's compiling against this. The law of Demeter. So the basic idea is that how far you should go from a particular function, right? How far should you go to talk to other things, right? For instance, being able to, is it okay from one function to call another function in the same class? Well, that makes sense, right? That you should be able to do that. That's kind of natural. If somebody passes you a parameter, right? Perhaps that makes sense that you should be able to call functions on that parameter that's being passed to you, right? So this law of talking to friends, not talking to stranger, kind of is a principle that dictates how far you should go away from the current place that you're locally implementing. So let's take a look at some of these ideas of the call your friends, don't talk to strangers. So certainly you should be able to call itself things that are declared within your sphere of scope, or any parameters that are being passed to you. Or any object that you instantiate, right, yourself, any object that you call new on, right, or that somehow you have a reference, somebody passed you a reference, right, and you have access to them. So some very simple ideas. Here you have a university class that gives you access to a professor. Here you're instantiating a boring professor. Okay, so get professor returns boring, and get new professor just instantiates a new professor. So here you have a task that is accessing the university class. So this would be discouraged, right? Where you have an instance, a local instance. So it would be okay for you to call the method on an object for which you have an instance, right? But it would not be okay, according to this principle, that once you have this object, you would then call on that, right? So this would be considered to be a stranger to you, right? So you also refer to this principle as the one dot principle. So you should only ever go just one dot away from where you are, right? If you want to go further, way, then you should explicitly make instances declared here, so that you're explicitly declaring an interest in some of these instances. So this certainly would be discouraged under this principle, right? That you would be going more than one hop away from the variable. So if you indeed wanted to implement this, right, instead you would the other class would implement a function that would explicitly access the data set, so that it would not force you to go 2 hops away, right? So it would be just UDS dot fire professor, and then the other class would actually implement that, right? So this tends or forces you to write your code in such a way that it's easier to read, right? It's easier to maintain, and for other folks to come in and it makes it self-documenting. Here's another example of here you have a private variable topping, a cheese topping, and you have a function down here declared in the same class, right? So would it be okay to call your own function? Yes, that's okay, right? Calling the do something. So from within your good pizza function, it is okay to call do something. Yeah, that makes sense. Would it be okay to call the on the pizza parameter? It would be okay to call a function on that parameter that's being passed to you. That would be okay as well. Or any new instances that you create, right? Any local instances that you create also would be okay to call functions on that class. Either because somebody passed you an instance of the cheese topping, or because you instantiated it yourself, right? That you would call a function on that, right? But it would not be okay, right? That you have an instance of an object A, and then you try to navigate down to get object B, and then do something under there. Even worse, right? You have 2 or 3 hops away from where you started. So this principle would discourage source code that is written that way. So the idea is that these 2 or 3 principles that we looked at would reduce the coupling. It would disallow access to different parts and limit the accessibility of the classes. Right? It would force you to think about it. How else should you wrap the behavior so that it encapsulates the entire behavior in an explicit function, as opposed to spreading it across multiple places, right? Imagine if you were doing this over and over. If you find yourself doing this over and over, right? Then perhaps the function should give you an abstraction that allows you to do this, right? It means that your abstraction layer is not abstract enough, right? That if you do it once, but if you find yourself doing it over and over, it immediately should be some bells should ring, right? That perhaps the object A should somehow do something, right? Or give you access to that behavior. It should be done inside of the get object B should do that. Then we have hierarchies. So hierarchies again allows us to break up the system into multiple layers of abstraction and also promote reusability. The most common reusability technique that we typically use is the inheritance, right? Where we declare a base class, and then we extend that class, right? That we inherit functions that are declared on the base classes. But it's not the only mechanism for reusability. Certainly, we can use composition and aggregation and many other techniques. The thing is that the reason inheritance seems to be the more obvious, right, is that it's explicitly supported by object-oriented programming languages, right? The syntax is there, right? You say extends and then the base class, right, or colon and the base class. The language already supports the syntax in a very clean way, and once you do that, then you get a lot of free stuff, right? You get polymorphism, right? you get inheritance, you get overriding, overloading. All these behaviors are immediately supported for you, right? Other ways of creating hierarchies like composition and aggregation are not as well supported in languages. You don't really get any special treatment if you implement aggregation, even though it might be a better solution than doing inheritance, right? It's not. I mean, obviously you can implement it, but it doesn't have a special syntax, right? Nothing. There's no magical syntax that supports the use of aggregation and composition. So there's two main ways of which we can implement different hierarchies. The more common one that we all are familiar with is a hierarchy, right? Where we create a base model of some abstract idea, right? And then we progressively create a more specialized version of that initial base class, right? And the idea would be that any progressive classes would be adding, right? Would be adding behavior, would be adding more support for more data, more specific data, but nonetheless would still support the base implementation of higher classes, right? You should be able to have a class that extends a base class still behave like a base class, right? So if you have if a rectangle if a square is a rectangle, right? Then any behaviors that were supported by the rectangle should still be supported by the square, right? Even though the square is the most specialized version of a rectangle, right? So anywhere where I can put a rectangle, I should also be able to put a square, right? So it should be able to add new things, and not remove anything that was already there. Okay. So other ways of implementing hierarchies is through the aggregation, where a class might have instances of other classes as part of its declaration, where the example car has 3 to 4 wheels. Oftentimes, this is a better implementation of creating hierarchies, right? Where class A has B and C, and then B then has C, E and F, and Av has M and N, right? So you can create a hierarchy of these things that might be a better choice than using generalization, right? Although generalization for creating hierarchies has often been the go-to place to go, right? The default way of building different hierarchies. But oftentimes, aggregation is a better solution. So the hierarchy principles. Some of the principles that we might want to consider when implementing these hierarchies are some have some famous names, such as the open and closed principles that classes in general should be open to be extended, right? That you should be able to declare a more special version of the base class, but it should not allow you to modify the original declaration of your parent. Okay, so that you can still behave like your parent, right? If you're treated like an adult, you should still support any of the any behaviors that you were extending. Another one is the Liskov substitution principle, again, where any subclass that is extending a superclass should be able to substitute for its base class, right? You should be able to replace anywhere where a rectangle falls, I should be able to replace it with a square, and it should still behave the same. And the other principle that it's a little more more modern, and it's widely used in J2EE and now in some of these newer MVC libraries, is the inversion of control, right? That we are inverting a bit the way we manage the life cycle of a class, of an object, right? Typically, it would be the parent that would be responsible for the life cycle of any children, right? It instantiates them, creates new instances, right? it uses them and then maybe throws them away or collects them and whatnot. So in inversion of control, typically we remove that responsibility away from the parent, right? It's no longer the responsibility of the parent to instantiate any of their classes. Instead, we delegate that to either a constructor, right, or we delegate it to some infrastructure that by the time the parent is instantiated, all the dependencies are also instantiated. They're already passed in, already instantiated, right? So no longer is the parent responsible for managing the lifespan of its children, right? One of the more common uses of this is when you have a service layer that is talking to a data layer. It's a very common thing that especially if you are in a multi-threaded environment where you have that you have hundreds or thousands of threads running through your source code. It would be very, very expensive to instantiate a database connection every single time. So more typically, that is the life cycle management of those database connections is delegated to the infrastructure, right? To the servers, delegated to the server, so that when the server boots up, right, it's its responsibility to instantiate 10, 20, 30, 100 connections, yes? Puts them in a pool, and then by the time you want to connect to the database, you don't have to instantiate. It's not your responsibility. Somebody magically passes you an instance of the connection, right? And then you talk to the database, and when you're done, you just release the connection. And the connection is then ready to be used by the next thread. So that's a very typical instance. Same thing with services. Services also, typically they're implemented to be singletons, right? Where you have a single instance of a service. Again, a very, very expensive object to instantiate, right? So instead of instantiating and releasing and instantiating again, typically they're instantiated only once, made available in a very well-known place, typically maybe JNDI or some naming service, right? And then you ask for it by name, or you ask it to be injected, or ask it to be passed in as in the constructor, right? So that by the time I'm constructed, whatever dependencies I might have are passed in into the constructor, right? And so that when I need the service, I'll have it right in my constructor, so that I can then use it, and then just stop using it. I don't need to instantiate it. If somebody else was responsible for instantiating. So so dependency inversion principle right now it has become a very well documented, a very well mature technique in modern languages, right? So certainly Java, .NET, and also certainly in the client side, also Angular certainly uses inversion of control, pretty heavily, right? And it's a very common technique. So the open closed principle is that the class should allow to be extended, right? To add new functions, add new behaviors, add new variables. It would be useless to extend the class, but then don't add any new behavior, right? It's with the intent of creating a more special version of the previous class, and typically it's implemented or achieved through inheritance or dynamic binding. So let's look at examples, right, of some of the reasons of creating these, right, of creating this, be able to reusability in these hierarchies that allow us to create these modules that are implemented, that they can be reused. Without hierarchies, you would have lots of these types of code, right, where you would have lots of if-else or lots of switch case statements all over your source code, right? That your source code would look at a particular data type, and based on some that data type, it would decide to go one way or another, right? To behave one way or behave another way, right? And you have lots of these switch case statements all over your source code, right? And the way we've been able to remove these switch cases, right, is through inheritance, right? Is to say, oh, wait a minute, so you want to connect, and there are actually different types of connections, but they're all connections. They're all connections, and it could be through an Ethernet or WAN, LAN or modem and whatnot. And wouldn't it be great, right? So that instead of having this if-else spread all over the place, right? Because this if-else structure would be replaced. It would be copied and pasted everywhere, where we have connect, close, write, read, right? Purge, flush, all these API, right? Of talking to these connections would have different implementations depending on the type of connection you're talking to, right? And each one of them would have something similar, right? Where you would have lots of these if-else and switch cases all over the place. It would be a nightmare to maintain this, right? If you have to change something in one switch case statement, you need to change it for all of them, right? So you would have this spread all over your source code. So the way we solved this was to delegate a lot of this mechanism of switch of else if and switching to the infrastructure, to the language, right? And created abstraction layers over that. And we said, okay, well, what if instead, right? We had some abstract connection, right? And somehow automatically, right? That connection is already of the right data type, right? It is already a modem connection, or it's already an Ethernet connection, and somehow magically when I call connect, right, it would know, which one to call. Can we somehow take all this else if, right, and put it inside of this magical connect function, and then the connect function, right, can then decide which one to call, right? So instead of me writing it, right, the compiler will write this for me. Okay, and that was the idea of polymorphism and adding, with hierarchies and inheritance, right, and having multiple classes inheriting from one base class, right, of delegating all this work, right, to the compiler, right. We just had to have the syntax to tell the compiler what we wanted to do. And so in an abstract sense and graphically, this is what we meant, right, where we have this base class, and then we would have the individual implementations of connecting either LAN, Ethernet, or modem, and each one knew the specific implementations of their connect, hang up, flush and purge and whatnot, right? All these APIs, and then we would have to come up with the syntax, right, to declare these things, right? We would have an abstract connection class. That wouldn't actually have the implementation, but then you would have the concrete classes extending them and actually implementing the various versions of the connect, so that once we've done this, right, the rest of the source code could deal with the abstract connection, wouldn't have to deal with the individual instances, right? It would magically bind at runtime which version it was that you were passing along, right? And that's the beauty of overloading. Same thing, another example of a billing where you might have, you need to compute maybe either a bill or a payroll system, right, depending on the type of employee. If you're a salaried employee, if you're a hourly employee, if you're a contractor or part-time and whatnot, having to compute these would be depending on the type, right? Your hourly rate, your yearly pay and whatnot, or a compute bill, right? Depending on the billing, whether it's business or function 120 and whatnot, or the year, the contract, and so all these rules, all these business rules would be implemented in specialized classes that would inherit from the plan. An abstract plan, right, that would keep track of different discount rates and different billing increments, and they would implement the rules based on the plan. The other principle, the Liskov substitution principle, kind of states that if you have an abstract class and then you have a more specialized class, you should be able to substitute them. You should be able to grab that, whenever you have a the use of a abstract class, you should be able to just plug and play a subclass in its place, right? That the derived methods should still support the base implementation, right? Presumably the derived methods would be smart enough to deal with a more specialized version of the more generic abstract class, but they should still be able to support that if they don't have that kind of specialized data, they should gracefully still support the more abstract implementation. One example on where the idea where that this would not be the case and would be a bad decision of inheritance, even though at the beginning might look trivial and self-evident, is that you might have a base class of ellipses, right, and immediately decide that circle is a special case of ellipses, right? That anywhere where you have a circle, I should be able to plug in ellipses, and that's not the case, right? Because ellipses has many more behaviors, right? Many more pieces of data that would be inherited by circle. That circle would not be able to support because it doesn't have two radiuses, right? It doesn't have the some of the information that would need to be able to support the implementation of an ellipses, right? It only has one radius, right? I don't have the second radius to be able to calculate any of the other pieces of information, right? So this would evidence a bad choice of inheritance. So dependency inversion principle was the what I mentioned earlier, right? Was the notion of that who should be the responsible for managing the life cycle of certain instances, right? And oftentimes we would find source code that was heavily dependent, right? That I had to instantiate it, I called the methods on the function, and then I released it, right? I was very tightly coupled with the lifespan of this object, right? With the inversion of control or dependency injection, right, we kind of went away from that idea, right? That you no longer were responsible for managing the lifespan. Instead, some higher abstraction was responsible for passing you these instances. You were responsible for using it and then just releasing it. You didn't manage this, right? So in this case, you became decoupled, right, from having to deal with these other instances, right? It also allowed you to kind of be able to someone else decide what to pass you, right? It made it easier to, for instance, test, right? So, for instance, how might you test a service layer that or business layer that independently of all the dependencies, right? Business layer might depend on a service layer, and the service layer will depend on the data layer, and the data layer assumes that there's a database, right? So if they all are coupled with one another, how do you test them independently, right? So ideally, you should be able to inject those dependencies, right? That they're not tightly coupled. They're not responsible for So the business layer would not necessarily instantiate the data layer. The data layer not necessarily would actually connect to a database, right? But you still want to test it, so you should be able to pass in, right, the service layer or the data layer to test it independently, so that you can mock it, right? You can make it think that it's talking to the real thing, right? But you actually control that, right? So that when it's calling, a select star from whatever, right? I can actually return a dummy set of data, right, from using a mock injected version of this, right? And then I can see whether it's iterating correctly, if it's sorting correctly, whether it's independently of all the dependencies that it might depend on, right? So inversion of control really opened up a lot of capabilities of us improving the quality of our source code, right? That we could certainly test our controllers, our user interfaces, our services, right, independently, right, of all the other of all the things that would need to depend, right? Because we could inject these things the test harness, right, could inject all the dependencies, and so that the code under test, right, would behave just the same way that it would behave when it was actually running in real time, right? So dependent injection allowed you really to improve our data, our source code quality. So here's an example of how we would normally implement something here, where you would have maybe a manager, right, that is tightly coupled over here. Is tightly coupled with the instance of worker, right, where we call a worker and is being passed to us in a set worker, and then we call worker.work. And it's tightly coupled with worker being of type worker, right? So you can only talk to that worker over there. It cannot, for instance, talk to these super worker, even though it has the same. It also has a work function, right? So to kind of decouple this, instead what we do is that the manager doesn't actually talk to any one individual worker or any specific type of worker. Instead, they compile against an interface, right? An interface that abstractly implements the work function, right? And that work function will be dynamically bound, right, at runtime. So at runtime, we will know which actual work function are you calling, right? Not at compile time, right? Because at runtime, we could decide to pass you a super worker or just a normal worker, right? Both of them implementing the iWorker interface, right? So the compiler looks at this and says, oh, okay, well, I have the workers of type iWorker. This work, right, I won't know which one to call until at runtime. At runtime, I will know if worker is actually of type superworker or is it of type worker. And then this syntax will know to call one or the other. So what we've basically done is that this decision of which one to call is actually implemented by the compiler, right, inside of this work function. This work function tests to see the type of, and then it calls one or the other. Right? So it has been abstracted for us by the compiler. Another example, very common when you have, in a multi-layered implementation, either an MVC or where you have a data layer or a service layer, maybe a controller layer. Typically, the service layer needs to have access to the data layer, right? So that if it passes some data, you want to be able to store that data in the data layer. So to be able to access the data layer, we would need to perhaps instantiate the data layer, right? And then we would call the data layer store, where the data layer is down here, store, right? And same thing with the controller. The controller also would need to control the life cycle of the service layer, right? So typically we've moved away from this type of code, right? This would no longer be acceptable, right? Typically, if we delegate the management, the life cycle management of the data layer, of the service layer, we leave it up to the infrastructure, right? We leave it up to a server, leave it up to some framework who will instantiate these, right, at runtime, and it will pass it to us, right, through any number of mechanisms, either in the constructor, right? We could say pass it to me in the constructor, or pass it to me as an auto wire, right? If you're using Spring MVC, or some other inversion of control. So typically you would see something like this, where these now become kind of singletons, right? The data layer becomes a singleton. The service layer becomes a singleton that can be injected, right? They're now injectables, right? That can be passed in either in a constructor like this, right? As the service gets passed in, the data layer also gets injected into the service layer. So we're not responsible for instantiating these things. Somebody magically instantiated these things, right? And it's keeping track. It's maintaining a cache version of this, right? Making sure that this is actually connected to the database and whatnot. All these things are being delegated. All the details of managing that have been abstracted out for us. Right. So again, this is a more common syntax for today. Right, choosing abstraction. We talked about this, and that depending on where you fit in the abstraction layer of dealing the problem with the right abstraction, and all of it, all these techniques have the intention or goal of making the source more maintainable, more reusable, that you can easily move things around, and that you're not tightly coupled with these other things, right? That if you move things around, they don't compile anymore, right? Ideally, you like to be able to move these things around, and it makes it easier to maintain. So a couple other things we mentioned earlier that there were a couple of ways of dealing with hierarchies. We mentioned inheritance. Certainly, it seems to be like the default way we implement these hierarchies. But certainly, composition is might be a better choice in certain or even the delegates is also a design pattern that has become very, very popular today. So let's just compare the two. Where inheritance, you would have this implementation is a very common way to create hierarchies, right? Where you have a chain of inheritance, where you have a base class A, and then B extends A, and either overrides F or overloads overloads or overrides or adds new functions. Now one of the negative aspects of this is that A not only is it inheriting F, right, but it also might be inheriting a whole bunch of other things that it didn't care to inherit, right? It has complete access to its parent, right? Unless you've perhaps gone through and declare certain things to be protected, that children should not inherit certain things. But nevertheless, it has typically has access to the data types, right? All any variables that it might depend on, right? And oftentimes this is not desirable, right? That it has unfettered access to the implementation of certain things. That it might because it's part of the family, part of the inheritance family, right? It has direct access to some of the data structures. That it knows that you're using a linked list, right? That it knows that you're using a set or a hash table or whatever, right? And now because it now becomes tightly coupled with that implementation, right? So any decisions that class B might do on the implementation will have done it by breaking the information hiding principle, right? That now any source code that you write is dependent on the original implementation. That no longer can you change A, right, without breaking B. Right? So oftentimes this implementation, right, is oftentimes referred to as, yes, you are reusing, but you're white box reusing. You know what you're reusing, and you might break the some of the principles that we wanted to look at. A different implementation might be that instead we use composition, where you have a reference to a class, right, that implements a particular interface, and then you use that function. But now you've decoupled it. A can now change the implementation of F without B having to explicitly know how that particular implementation was done, right? Now one of the negatives is that the language doesn't you don't get anything new from here. This is obviously supported, but there's no syntax that makes this any easier, right? Whereas the syntax of just extends, that's a very powerful word, right? A lot of magical things happen when you extends, right? Polymorphism and overriding and overloading, all these things are supported just with this one word. Over here, there's no special treatment for a composition, right? So you're all kind of on your own, right? Of implementing composition and following good practice. So class A, class B, it's very simple, very easy to implement. Just override a couple of methods and you're done. But it kind of breaks the principle of encapsulation, breaks the principle of information hiding, So lots and lots of things go out the door. You inherit a lot of things that you didn't care for, and now you're responsible for. And that perhaps a better choice is to instead use interfaces, right? A implements I, and B only has access to A through an interface. Okay? And again, it's a black box. You don't get access to the internal details, and they're still decoupled. You can change A without breaking B. Right. So in general, the overall principle is to not compile to an actual implementation, but instead compile to an interface, right? And that keeps the reusability and the decoupling alive, right? Another principle is the principle of delegates, right? Where instead of you directly using a particular function, instead you declare a separate function that actually does the work, right? And so you create either instances of that, or they're being passed to you through injection, and then you use that function to actually implement it, right? Again, this decouples it so that I'm not directly dependent on the implementation of D, and that the D actually delegates and implements all those implementations. They kind of forward the methods over to another class that is responsible for implementing them. Here's another example where typically you would the way you would implement this is that but I think there's two, right? Yeah. So normally you would perhaps have a printer, and the tester implements, instantiates the printer, and it calls print on it, right? So here it is where you would implement it using inheritance, right? You would extend real printer, and the print is not actually implemented by printer. Instead, it uses a delegate real printer who actually does the printing, right? And using composition, instead of extending, we can use a delegate, right? Instead of doing the extension, we can use a delegate. We can do an instance of the real printer and then call p.print, right? As opposed to extending it. If I extend it, then I have direct access to the implementation of real printer, which I don't want to be coupled with. Instead of I'm delegating and not extending it. Okay. Stack. Here's an example of why inheritance sometimes breaks, and what are the consequences. So here's a stack implementation. Internally, the stack uses a vector, right? But the stack has a particular implementation, right? And ideally, it would behave where only the modifications happen in on one of the sides of the stack, right? At the top of the stack. You either push or pull, right? Or pop the stack. You would never, for instance, manipulate the stack in the middle, right? But internally, it's implemented using a vector, right? And it has the push and pop, and this is fine, right? But now, if somebody comes along and inherits from this, right, a bad stack, who inherits from vector, wait a minute, let's see. Bad stack, push, add. I thought there was another version of this where I extended stack. Anyway, the idea was that it was extending stack, right? And because it was extending stack, it had access to the vector that it was using underneath, and because it knew it was a vector, it could start doing some bad things, right? Maybe inadvertently start manipulating the stack in the middle, right? You're extracting things from the middle. That it's no longer considered to be a stack, but that's only because it has private access, right, to some of the detailed implementation of the original stack that is extending, right? And so a better implementation would be to use delegates instead of or interfaces instead of having used inheritance. Even some of the Java libraries, made this mistake early on, implementing some of their own data types, and because once it was out there, folks had already used the library. Fixing it, implementing it correctly would have broken lots of other folks that were extending those stacks, and we're expecting that it was implemented using a vector, right? So they could no longer backtrack since they would break anything for backward compatibility. Yes. Yeah. This one?
No, the only one. One slide back before this.
Yeah.
In the second class, the printer class, it's using super.print to call the real printer method. But if you go to the next slide, you're actually creating the object of real printer and then calling it differently. So is that something you need to delegate, or it just in the printer class?
What do you mean?
So here you're creating an object of real printer, right?
Yeah, yeah.
And then you're calling the method from that class.
Yeah, right.
Yeah, and you're not using extends.
Right, we're not using extend.
And in the earlier example, you were actually using extends and then calling it based on the
Right. Yeah.
So that's specific. This is specific to the delegates, right?
Yes. Yeah. So the idea was to use a delegate as opposed to an extend.
Yeah.
So that you don't have access to the private implementation of whatever the printer is doing, right? That was the point I was trying to make. Yeah. All right. So I think I'm done. All right. So let's take a quick break, and we'll come back right after these messages.